Welcome to Sleepy Science Stories. I'm so glad you're here. Before we begin, I'm curious, where are you watching this from? And what time is it where you are? Whether you're tucked in bed as the day winds down, or perhaps it's the middle of the night and sleep eludes you, you're exactly where you need to be. Tonight's journey will take us through the gentle realm of science and wonder. No rushing, no urgency. Just a slow, peaceful exploration designed to ease your mind and guide you toward rest. So find your most comfortable position. Let your body sink into wherever you're resting. Take a slow, deep breath, and another. Tonight we explore one of the universe's most profound transformations, the death of stars. Not with alarm or fear, but with the wonder that comes from understanding our cosmic home. We'll witness the gentle fading of some stars, the spectacular explosions of others, and the strange, almost impossible objects they leave behind. Look up at the night sky on any clear evening, and you'll see what appears to be eternal. Stars twinkling in their ancient patterns, steady and unchanging. Our ancestors watched these same points of light, and their ancestors before them. The constellations seem permanent, written into the fabric of night itself. But appearances, as so often in science, tell only part of the story. Every star you see is burning fuel. Not the way a candle burns, consuming wax and oxygen, but through a process far more fundamental, one that transforms the very fabric of matter itself. This burning cannot last forever. Even the universe, it seems, has its limits. Each star carries within it the seeds of its own ending, written into its nature from the moment of its birth. The smallest stars will burn for trillions of years, far longer than the current age of our universe. Larger stars, paradoxically, live fast and die young, some lasting only a few million years before their spectacular end. Size, in the cosmos, dictates destiny. The mass of a star determines not just how long it will shine, but how it will die and what strange remnant it might leave behind. You might wonder how we could possibly know this. After all, human lifetimes are brief, barely a cosmic heartbeat. We've watched the stars for a few thousand years at most with any careful attention. How can we claim to understand processes that take millions, even billions of years to unfold? The answer lies in numbers. Our galaxy alone contains hundreds of billions of stars, each at a different stage of its life. Some are newborns, still swaddled in the gas clouds of their birth. Others are in their stable middle age, like our sun, steadily fusing hydrogen into helium. And still others are approaching their end, their fuel running low, their cores growing desperate. By observing countless stars at different stages, astronomers have pieced together the story of stellar death, a biography written in light across the cosmos. It's rather like watching a forest, if you think about it. You might never see a particular tree grow from seed to ancient oak, but by observing thousands of trees of different ages, you can understand the entire life cycle. The deaths of stars are not simple affairs. There is no single path that all stars follow. Instead, stellar death comes in varieties, each with its own character, its own physics, its own aftermath. Small stars fade gently, cooling over eons into crystalline spheres. Massive stars die in explosions so powerful, they briefly outshine entire galaxies. And the most massive stars of all might collapse into objects so dense, so strange, that they break our intuitive understanding of matter and space itself. Tonight, we'll walk through these endings, one by one, at a pace that allows for reflection and wonder. We'll visit dying stars and their strange remnants. We'll explore the physics that governs their final moments. Physics so extreme it seems almost fictional, yet is grounded in observation and mathematical certainty. There's something oddly comforting, I think, about understanding endings. The universe wastes nothing. When stars die, they seed the cosmos with the elements forged in their cores. The carbon in your body, the iron in your blood, the calcium in your bones, all were created in stellar furnaces and released by dying stars. We are, quite literally, made of stardust. The death of stars is not an ending so much as a transformation, a passing of materials from one generation to the next. As we begin this journey, let your breathing slow and deepen. There's no test at the end, no need to remember every detail. Let the information wash over you like gentle waves. Some will stay with you, some will drift away. Both are perfectly fine. This is a story meant for the boundary between waking and sleep, where wonder and rest meet. The night sky above you, whether you can see it through your window or must imagine it, is filled with stars at every stage of life and death. Ancient light reaches your eyes, photons that began their journey long before you were born. Some stars you see tonight are already dead, their light still traveling toward us across the vast distances of space. Others are in their death throes right now, though we won't know it for years or centuries to come. In the chapters ahead, we'll slow down time itself. We'll watch processes that normally take millions of years, observing them with the patience of cosmic time. We'll shrink down to witness atoms crushed together in ways that don't happen anywhere on Earth. And we'll zoom out to see explosions that reshape galaxies. Through it all, let the rhythm of the narrative carry you. When your mind wanders, and it will, and should, that's fine. You can drift along with the story or let your thoughts meander. There's no wrong way to experience this journey. The death of stars awaits us, patient and eternal. Let's begin with the gentlest ending first, the fate of stars like our sun, which will someday fade into crystalline silence, a white dwarf cooling slowly in the cosmic dark. Chapter 2. The fuel of stars. To understand how stars die, we must first understand how they live. What keeps a star shining? What fuel powers that immense outpouring of light and heat that reaches across space to warm worlds and illuminate the darkness? The answer is both simple and profound. Stars shine because they are falling. Picture this. Deep within a star's core, gravity is always pulling inward. Every atom wants to fall toward the center. The star is in a constant state of collapse, held up only by the pressure created by its own tremendous heat. Remove that heat, and the star would implode in moments. It's a delicate balance. Gravity pulling in, pressure pushing out. The two forces locked in an ancient dance. This heat, this pressure, comes from nuclear fusion. At the core of a star, temperatures reach millions of degrees. Matter exists in a state called plasma, atoms stripped of their electrons, nuclei flying free, moving at tremendous speeds. In this maelstrom, atomic nuclei occasionally collide with enough force to overcome their natural repulsion and fuse together. You see, atomic nuclei all carry positive charges, and positive charges repel each other. It's like trying to push the north poles of two magnets together. They resist. Under normal circumstances, atomic nuclei would never touch. The electromagnetic force that makes them repel is extraordinarily strong. But in a stellar core, circumstances are far from normal. The temperature is so high, the nuclei are moving so fast, that when they collide, they sometimes overcome that repulsion through sheer kinetic energy. It's a bit like ramming two magnets together so hard they break through the magnetic field and stick. Not the most elegant analogy, perhaps, but it captures something of the violence involved. When nuclei fuse, something remarkable happens. The resulting nucleus weighs slightly less than the sum of its parts. That missing mass hasn't vanished. That would violate fundamental laws of physics. Instead, it's been converted directly into energy, according to Einstein's famous equation, E mx. A tiny amount of mass, multiplied by the speed of light squared a very large number, produces an enormous amount of energy. This energy radiates outward, creating the pressure that holds the star up against gravity's relentless pull. The star is, in essence, a controlled fusion reactor, massive beyond human comprehension, held together by its own gravity. Most stars, for most of their lives, fuse hydrogen into helium. Hydrogen is the simplest element, just one proton. When 4 hydrogen nuclei fuse together through a chain of reactions, they form one helium nucleus, 2 protons and 2 neutrons bound together. This is the reaction that powers our sun and has done so for about 4.6 billion years. It will continue to power the sun for another 5 billion years or so. This is not guesswork. We can calculate it quite precisely based on the sun's mass, its luminosity, and our understanding of nuclear physics. The math is reassuringly solid. But hydrogen doesn't last forever. As a star ages, its core gradually fills with helium, the ash of hydrogen fusion. You might think of it as a cosmic furnace slowly filling with its own spent fuel. For a while, this doesn't matter. There's plenty of hydrogen left to burn. The helium ash simply accumulates at the very center where gravity pulls it. Eventually, though, the hydrogen runs out. Or rather, the hydrogen in the core runs out. There's still plenty of hydrogen in the star's outer layers, but that's not hot enough or dense enough for fusion. The core, where conditions are most extreme, is now pure helium. And here, the fate of the star diverges based on its mass. Small stars, those less than about half the mass of our Sun, will never get hot enough to fuse helium. When their hydrogen runs out, they simply stop fusing. The pressure drops. Gravity wins. The star collapses, but gently, slowly, settling into a new equilibrium as what we call a white dwarf. We'll explore white dwarfs in detail in the coming chapters. For now, just note this: the smallest stars die quietly. Stars like our Sun, with moderate mass, can take the next step. As the hydrogen core is exhausted and begins to collapse, the compression heats it up. Counterintuitively, the star's outer layers expand and cool, turning the star into a red giant, huge, luminous, but with a relatively cool surface. Meanwhile, the core continues to collapse and heat until it reaches about 100 million degrees. At that temperature, helium fusion becomes possible. 3 helium nuclei can fuse to form carbon, releasing energy in the process. The star has found a second fuel source. It's a temporary reprieve, like finding emergency rations after your main supplies run out. Helium fusion doesn't last nearly as long as hydrogen fusion, perhaps only a few 100 million years for a Sun-like star, compared to 10 billion years of hydrogen burning. Larger stars can go further still. After helium comes carbon fusion, then neon, oxygen, silicon, each fusion cycle producing heavier elements and lasting for shorter periods. A massive star might fuse carbon for just a few thousand years, oxygen for a few months, silicon for a single day. The star is racing toward its end, burning through fuels ever more desperately. There's a limit to this process, though, a fundamental limit set by the physics of nuclear binding energy. That limit is iron. Iron sits at the peak of the binding energy curve. Fusing lighter elements into iron releases energy. Fusing iron into heavier elements requires energy. It's endothermic, not exothermic. An iron core is not fuel. It's a dead end. Once a star's core turns to iron, no fusion reaction can generate the pressure needed to hold up the star. For massive stars, this is the beginning of the end. But we're getting ahead of ourselves. Before we reach the dramatic deaths of massive stars, let's turn to gentler endings. Let's explore what happens to stars like our Sun when their fuel runs low and they face their final transformation into white dwarfs, objects so strange, so removed from everyday experience, that they seem almost impossible. Chapter 3. The fate of Sun-like stars 5 billion years from now. Give or take a few 100 million, our Sun will begin to die. This isn't cause for alarm. You won't be around to see it, nor will your descendants for many thousands of generations. But it's interesting to consider the fate of our home star, because its death will follow a pattern shared by the vast majority of stars in the universe. The process begins with exhaustion. After 10 billion years of steadily fusing hydrogen into helium, the Sun's core will finally run out of hydrogen fuel. The helium ash that has been accumulating at the center will constitute the entire core, inert, not fusing, no longer generating the pressure needed to support the star. Without that pressure, the core begins to collapse. Gravity, patient and relentless, finally gains ground in its eternal battle. As the core contracts, it heats up. Gravitational compression converts potential energy into thermal energy. This seems paradoxical at first. How can a collapsing, dying star get hotter? But it's a fundamental principle. Compress a gas, and it warms up. You experience this every time you use a bicycle pump. The pump gets warm as you compress air into the tire. The collapsing core doesn't reach fusion temperatures yet, but it does get hot enough to heat up the layers of hydrogen surrounding it. These layers, which were previously too cool and diffused to fuse, suddenly find themselves compressed and heated to the point where fusion becomes possible. The Sun will begin fusing hydrogen in a shell around its inert helium core. This shell fusion is vigorous, far more so than the core fusion that preceded it. the star begins to produce more energy than it did in its main sequence youth. That energy radiates outward, and here's where something strange happens. The outer layers of the star expand enormously. The sun will swell to perhaps 100 times its current diameter, maybe more. Its surface will cool as it expands, glowing red instead of yellow. The sun will become a red giant, vast, luminous, but with a relatively cool surface temperature of only 3,000,4,000 degrees Celsius compared to the 5,500 degrees it maintains today. Mercury will be engulfed. Venus will likely follow. Earth, well, that's uncertain. The calculations are tricky because the sun will lose mass as it becomes a red giant, which means Earth's orbit will expand outward. We might escape engulfment, but Earth's surface will be rendered uninhabitable regardless, scorched by the sun's increased luminosity. Imagine, if you can, that swollen red sun filling half the sky, its surface close enough to see the roiling convection cells that carry heat from the interior. The Earth, if it survives, will be a charred rock, its oceans long since boiled away, its atmosphere stripped into space. This red giant phase lasts for about 1 billion years for a sun-like star. That might seem like a long time, but it's nothing compared to the 10 billion years the star spent on the main sequence. Stellar death, while slow by human standards, is relatively quick on cosmic timescales. Throughout this time, the helium core continues to contract. Slowly, inexorably, gravity squeezes it tighter and tighter. The temperature climbs. 50 million degrees, 75 million degrees, still not hot enough for helium fusion. The core grows denser, its atoms packed closer together, until something peculiar starts to happen. The electrons in the core begin to resist being compressed any further. Not because of heat or molecular forces, but because of a quantum mechanical principle called the Pauli exclusion principle. This principle states, in essence, that no two electrons can occupy exactly the same quantum state in exactly the same place. As the core compresses and electrons are forced closer together, they run out of available quantum states. This creates what's called electron degeneracy pressure. It's a pressure that doesn't depend on temperature, which is unusual. Normal gas pressure increases with temperature. Heat a gas and pressure goes up. Cool it and pressure drops. But degenerate matter maintains its pressure regardless of temperature. The electrons simply cannot be compressed any further without violating fundamental quantum laws. For a while, this degeneracy pressure holds up the core, preventing further collapse. The core continues to heat up from the energy released by the hydrogen shell burning around it. Eventually, abruptly, actually, the core reaches about 100 million degrees. Helium fusion ignites. In a non-degenerate core, this would happen gradually. But in a degenerate core, something dramatic occurs. The fusion begins, releasing energy. But that energy doesn't immediately increase the pressure, remember. Degeneracy pressure doesn't depend on temperature. So the core doesn't expand and cool, which is what would normally regulate the fusion. Instead, the fusion rate increases, releasing more energy, which heats the core further, which increases the fusion rate further. It's a runaway process called the helium flash. For a few seconds, the core of the star produces as much energy as the entire galaxy. But this energy is absorbed by the outer layers of the star and doesn't blast them away. The helium flash is invisible from outside. It's a private apocalypse contained within the star's interior. Then suddenly the temperature gets high enough that the degeneracy is lifted. The electrons have enough energy to access higher quantum states. Normal thermal pressure takes over. The core expands slightly, the temperature drops, and the fusion rate stabilizes. The star has found a new equilibrium, steadily fusing helium into carbon and oxygen. This helium burning phase lasts for about 100 million years, a brief coda to the star's main life. During this time, the star actually shrinks somewhat from its red giant maximum, becoming slightly smaller and hotter. Astronomers call stars in this phase horizontal branch stars, based on where they appear on certain diagnostic diagrams. But helium, like hydrogen before it, is finite. Eventually, the core fills with carbon and oxygen ash. The helium is exhausted. And now, for a sun-like star, there is no next step. The core is not massive enough to compress and heat to the temperature needed for carbon fusion, about 600 million degrees. The stellar furnace has run out of viable fuel. The helium-burning shell moves outward, leaving behind an inert carbon-oxygen core. Above it, a hydrogen-burning shell continues to operate. The star becomes increasingly unstable, pulsating, throwing off its outer layers in a series of gentle eruptions. These expanding shells of gas create what we call a planetary nebula, not because it has anything to do with planets, but because through early telescopes, these nebulae look like planetary disks. Planetary nebulae are among the most beautiful objects in the cosmos. Shells and bubbles of glowing gas, illuminated by the hot core of the dying star at their center, painted in colors dictated by the specific atoms they contain. Oxygen glows blue-green. Hydrogen glows red. Nitrogen, sulfur, and other elements add their own hues. Each planetary nebula is unique, shaped by the star's rotation, magnetic fields, and whether it had a binary companion. But these nebulae are ephemeral. They expand and fade, mixing into the interstellar medium over a few tens of thousands of years. What remains at the center, exposed now for the first time in billions of years, is the core of the star. No longer hidden beneath layers of hydrogen and helium, the carbon-oxygen core stands naked to space. This core is extraordinarily hot, perhaps 100,000 degrees at its surface. But it is no longer fusing anything. It shines only from residual heat, radiating away the thermal energy built up over billions of years of fusion. Slowly, over billions more years, it will cool. This cooling ember, roughly the size of Earth but with about half the mass of the Sun, is a white dwarf. And it is one of the strangest objects in the universe, governed by physics that seem almost impossible. Let's explore these bizarre stellar remnants in the next chapter, where the quantum world meets the cosmic scale. Chapter 4. White Dwarfs. Stellar embers imagine holding a sugar cube. Nothing unusual about that. It fits easily in your palm, weighs perhaps a few grams. Now imagine that same sugar cube made of white dwarf material. It would weigh about as much as an elephant. This is the reality of white dwarfs, matter compressed to densities that seem impossible, held up not by any familiar force, but by quantum mechanical effects that prevent electrons from occupying the same space. They are the most common endpoint of stellar evolution, the fate awaiting about 97% of all stars, including our Sun. And they are utterly unlike anything in our everyday experience. Let's start with the basics. A typical white dwarf has about half to two-thirds the mass of our Sun, compressed into a sphere roughly the size of Earth. Do the math, and you get densities around 1,000,000 times that of water. A teaspoon of white dwarf material would weigh several tons. How is this possible? How can matter be compressed so tightly? The answer lies in empty space, or rather, the vast amount of empty space that exists in normal matter. Atoms are mostly empty. The nucleus occupies an incredibly tiny fraction of the atom's volume. Most of the atom is just the electron cloud surrounding that nucleus. If an atom were scaled up to the size of a football stadium, the nucleus would be about the size of a pea at the center. In normal matter, atoms maintain their distance from each other. The electron clouds repel each other through electromagnetic forces, keeping atoms separated. But in a white dwarf, gravity has become so strong that it crushes atoms together. The electron clouds overlap, interpenetrate, forced into the same space. At this point, you might expect the electrons to occupy the same quantum states, packed together like commuters in a crowded train. But quantum mechanics forbids this. The Pauli exclusion principle states that no two fermions, and electrons are fermions, can occupy the same quantum state in the same place. The electrons resist, not through thermal motion, not through electromagnetic repulsion, but through a purely quantum mechanical effect. They generate what's called electron degeneracy pressure. This pressure depends only on density, not on temperature. Even if you could somehow cool a white dwarf to absolute zero, which you can't, but imagine if you could, it would maintain the same pressure, the same resistance to compression. This degeneracy pressure is what holds up a white dwarf against gravity. The star is in equilibrium, but it's an equilibrium quite different from that of a normal star. There's no fusion, no temperature-dependent pressure, just the quantum mechanical resistance of electrons to being confined in the same space. Here's something remarkable: white dwarfs get smaller as they get more massive. This seems backwards at first. Add more mass to a planet, and it gets bigger, right? Add more mass to a main sequence star, and it expands. But add more mass to a white dwarf, and it shrinks. Why? Because the additional mass means additional gravity, which compresses the star more tightly. The degeneracy pressure increases as density increases, but not as quickly as gravity increases with mass. So the star must compress to a higher density to maintain equilibrium. More massive white dwarfs are smaller. This has an interesting consequence. There's a maximum mass for a white dwarf, a limit beyond which even electron degeneracy pressure cannot support the star. This limit, calculated by Subrahmanyan Chandrasekhar in the 1930s, is about 1.4 times the mass of the Sun. It's called the Chandrasekhar limit, and it's one of the most important numbers in astrophysics. A white dwarf with exactly this mass would have zero radius. It would be compressed to a point. Obviously, this can't happen. Instead, if a white dwarf approaches this mass, something else must occur. The electrons, pressed together beyond endurance, merge with protons in the nuclei to form neutrons. The star undergoes catastrophic collapse, transforming into something even stranger, a neutron star. But that's a story for later chapters. Most white dwarfs are comfortably below the Chandrasekhar limit. They sit in space, slowly cooling, slowly fading. And the cooling process is extraordinarily slow. A white dwarf starts out hot, perhaps 100,000 degrees at its surface, even hotter in its interior. It glows brilliant white, hence the name. But with no internal energy source, no fusion to replenish heat, it can only cool by radiating that heat into space. And space, being nearly a vacuum, is an excellent insulator. The white dwarf cools slowly, taking millions of years to drop from white hot to yellow hot, then to red hot. Eventually, over billions of years, it will cool to the point where it no longer glows visibly. At that point, it becomes what astronomers call a black dwarf: cold, dark, crystalline. Here's the thing, though. The universe isn't old enough yet for any black dwarfs to exist. The oldest white dwarfs we can observe are still glowing faintly, still radiating their primordial heat. Calculations suggest it takes about 10 to 15 billion years for a white dwarf to cool to the point of invisibility. The universe is only 13.8 billion years old, and the first stars didn't form until it was a few 100 million years old at least. So even the very oldest white dwarfs are still warm enough to emit some light. Black dwarfs are theoretical objects, predicted but not yet observed. They will exist eventually, when the universe is much older than it is now. They will be among the most common objects in the far future cosmos: dark, dense spheres of carbon and oxygen, crystallized into cosmic diamonds, drifting through the cold and empty space between dying galaxies. But even white dwarfs that are still glowing present us with strange phenomena. As they cool, they undergo phase transitions. The carbon and oxygen in their cores begin to crystallize, forming a lattice structure, essentially a massive cosmic crystal. The crystallization releases latent heat, temporarily slowing the cooling process. Recent observations have confirmed this effect, observing white dwarfs that appear slightly warmer than they should be for their age. The explanation is that they're undergoing crystallization, releasing gravitational energy stored in the liquid interior as it freezes into a solid lattice. Imagine that. Stars turning into giant cosmic gems, their cores arranged in perfect crystalline order. It's almost poetic. These dead stars, embers of fusion's fire, transforming in their final long twilight into structures of exquisite regularity and beauty, even if no eye will ever see them directly. White dwarfs can also exhibit other peculiarities. Some have strong magnetic fields, thousands or even millions of times stronger than Earth's field. These are remnants of the original star's magnetic field, compressed and intensified as the core collapsed. These magnetic white dwarfs can affect matter falling onto them, channeling it along magnetic field lines to the magnetic poles. Speaking of matter falling onto white dwarfs, this brings us to one of the more dramatic aspects of white dwarf existence. Many white dwarfs are in binary systems, orbiting another star. If that companion star is close enough and evolved enough, perhaps a red giant with an extended envelope, matter can flow from the companion onto the white dwarf. This matter doesn't just splat onto the surface. It carries angular momentum, so it goes into orbit around the white dwarf, forming what's called an accretion disk. The disk is heated by friction and gravitational compression, glowing brilliantly in X-rays and ultraviolet light. From certain angles, you'd see a bright disk surrounding the white dwarf, feeding it matter from its companion. As matter accumulates on the white dwarf's surface, it gets compressed and heated by the white dwarf's gravity. Eventually, conditions become hot enough for fusion, not in the core, but right there on the surface. Hydrogen fusion ignites in the accreted layer, and because it's happening on the surface of a degenerate object, the conditions are ripe for a runaway reaction. The result is a nova, a sudden brightening of the star system as the surface layer explodes. Not the whole star, mind you, just the recently accreted material. The white dwarf itself remains intact. A nova can brighten a star system by factors of thousands or even millions, making previously invisible systems suddenly bright enough to see with the naked eye. Novae were historical mysteries, new stars appearing where none had been before. Now we understand them as recycling events in binary star systems, white dwarfs periodically shrugging off accumulated material in thermonuclear explosions. The same system can nova multiple times, as long as the companion keeps feeding it matter. But if the white dwarf accumulates enough mass, if it approaches that critical Chandrasekhar limit of 1.4 solar masses, something far more dramatic can occur. This is the realm of Type Ia supernovae, cosmic explosions so powerful and so consistent that astronomers use them as standard candles to measure the distance to galaxies billions of light years away. We'll explore these cataclysmic events in a later chapter. For now, rest in the strange piece of white dwarf existence. These stellar embers, patient and persistent, cooling over timescales that dwarf human comprehension. They represent the most common fate of stars, the destiny awaiting our own sun. And while that fate lies billions of years in the future, there's something profound about knowing the path ahead, understanding the transformation that awaits the star that has warmed our world for all of life's history. Chapter 5. The Quantum Physics of Stellar Remnants. Perhaps you've noticed that the death of stars seems to involve a lot of quantum mechanics. This might seem odd at first. Quantum mechanics is usually the physics of the very small atoms, molecules, subatomic particles. Why should it matter for objects the size of planets or larger? The answer is deeply beautiful, and it reveals something profound about the connection between the microscopic and the cosmic. Quantum mechanics doesn't just govern the small, it governs everything. It's just that in everyday life, and even in most astronomical objects, quantum effects average out or remain hidden beneath more familiar forces. But in extreme conditions, like those in the cores of white dwarfs, or as we'll see, in neutron stars, quantum effects emerge on a grand scale. Let's think more carefully about electron degeneracy pressure, because understanding it helps illuminate why white dwarfs behave so strangely. In a normal gas, pressure arises from thermal motion. Atoms or molecules bounce around, colliding with each other and with the walls of their container. The faster they move, the higher the temperature, the more pressure they generate. Cool the gas down, and the pressure decreases. At absolute zero, if you could reach it, thermal pressure would vanish entirely. But in a white dwarf, the electrons are degenerate. They're packed so tightly that quantum effects dominate. Each electron occupies a specific quantum state, and the Pauli exclusion principle forbids two electrons from occupying the same state. This isn't a force in the traditional sense. It's more like a constraint, a rule that nature enforces absolutely. When you try to compress degenerate matter further, you're forcing electrons into a smaller space. But there are only so many quantum states available in that space. To fit all the electrons in, some must be promoted to higher energy states. This requires energy input. The resistance to compression, the degeneracy pressure, comes from this need to promote electrons to higher energy levels. Crucially, this pressure exists even at absolute zero. It's not thermal. It's purely quantum mechanical, arising from the wave-like nature of electrons and the exclusion principle. In a sense, the electrons are defending their individual identities, refusing to become indistinguishable from one another. This leads to that counterintuitive property we mentioned. White dwarfs get smaller as they get more massive. Add more mass and gravity pulls harder. The only way to achieve equilibrium is to compress the electrons further, forcing them into higher and higher energy states, generating higher and higher degeneracy pressure until it balances the increased gravity. But this can't continue indefinitely. There's a limit. As the electrons are squeezed into higher energy states, their energies approach and then exceed their rest mass energy, about 511 keV in particle physics units. At these energies, relativistic effects become important. The electrons are moving at appreciable fractions of the speed of light. Their mass increases, or more precisely, their relativistic momentum becomes significant, and the relationship between pressure and density changes. Subrahmanyan Chandrasekhar worked all this out in the early 1930s, while still a graduate student. He calculated that for white dwarfs above a certain mass, about 1.4 solar masses, even relativistic electron degeneracy pressure cannot support the star. The pressure simply can't increase fast enough with density to counterbalance gravity. This is the Chandrasekhar limit, and it's carved into the fabric of physics. No white dwarf can exceed this mass and remain stable. If a white dwarf somehow accretes enough matter to approach this limit, it will collapse. What it collapses into depends on the circumstances, sometimes a supernova, sometimes a neutron star. But it cannot remain a white dwarf. The existence of this limit has profound implications. It means white dwarfs have a maximum possible mass, regardless of the mass of the progenitor star, as long as the progenitor is below about 8 solar masses. Stars that die leaving behind cores more massive than the Chandrasekhar limit cannot become white dwarfs. They must transform into something else. Now, you might wonder, what are these quantum states we keep mentioning? What does it mean for an electron to occupy a quantum state? In quantum mechanics, particles don't have definite positions and velocities in the way macroscopic objects do. Instead, they're described by wave functions, mathematical objects that encode probabilities of where the particle might be found and what momentum it might have. The act of confining a particle to a smaller space restricts the possible wave functions it can have, which in turn restricts its possible energies and momenta. This is captured in the Heisenberg uncertainty principle. The more precisely you confine a particle's position by squeezing it into a smaller space, the more uncertain its momentum becomes. And if momentum is uncertain, it must have some average value. In a degenerate gas, where particles are confined to a very small volume, this translates into significant momentum and thus significant kinetic energy, even if the temperature is zero. It's this zero-point energy, this irreducible quantum mechanical energy that exists even at absolute zero, that creates degeneracy pressure. You can think of it as the electrons jiggling around due to quantum uncertainty, and this jiggling creates pressure. The more you squeeze, the more they jiggle. The more they jiggle, the more pressure they generate. This pressure doesn't depend on temperature because it arises from quantum uncertainty, not from thermal motion. All of this might sound abstract, but it has concrete consequences. White dwarfs exist because of electron degeneracy. Their sizes, their masses, their cooling rates, all are dictated by these quantum mechanical principles operating on stellar scales. The very fact that you can compress the mass of the Sun into the volume of the Earth is a testament to quantum mechanics. Without the Pauli exclusion principle, atoms would collapse, and matter as we know it couldn't exist. There's a deep connection here between the stability of everyday matter and the existence of white dwarfs. Both rely on the same physics. The reason you can't push your hand through a table is ultimately the same reason a white dwarf doesn't collapse: electron degeneracy. The electrons in the atoms of the table resist being compressed into the same space as the electrons in your hand. It's quantum mechanics, keeping the solid world solid. In a white dwarf, this effect is simply taken to an extreme. The electrons are packed much more tightly than in any material on Earth, but the principle is the same. It's all one physics, governing the small and the large, the everyday and the extreme. As we move forward to explore the depths of more massive stars, we'll encounter even more extreme forms of matter, where neutron degeneracy replaces electron degeneracy, and where the quantum world meets the gravitational in even more dramatic fashion. But for now, let the strangeness of white dwarfs settle in. These crystallizing spheres, held up by quantum mechanics, cooling slowly in the cosmic dark, they represent a bridge between the familiar physics of matter and the extreme physics of stellar remnants. They are, in a sense, the universe showing us that reality is stranger than we typically imagine, but stranger in comprehensible ways, governed by laws we can write down and calculate. There's comfort in that, I think. The universe is weird, but it's understandably weird, and that makes all the difference. Chapter 6. Massive stars and their brief lives. Not all stars are destined for the gentle fade into white dwarf oblivion. Some stars, the massive ones, those born with more than about 8 times the mass of our Sun, face far more dramatic endings. To understand these catastrophic deaths, we need to understand the lives of massive stars, which burn bright and fast, racing through their fuel reserves in what amounts to cosmic moments. Massive stars are rare. For every star more than 8 solar masses, there are hundreds of Sun-like stars. Yet massive stars play an outsized role in the cosmos. They produce most of the heavy elements, they shape the interstellar medium with their powerful winds and eventual explosions, and they leave behind the strangest remnants, neutron stars and black holes. Let's follow the life of a massive star, from birth to its inevitable dramatic end. Such a star forms in the same way all stars do, from a collapsing cloud of gas and dust in a stellar nursery. But from the beginning, mass changes everything. A massive star contracts more rapidly under its own stronger gravity. Its core heats up faster. Within perhaps just a few million years, a cosmic eye blink, the core reaches fusion temperatures, and the star begins its main sequence life. On the main sequence, it fuses hydrogen into helium just like smaller stars. But it does so prodigiously, at rates that dwarf the Sun's output. A star of 20 solar masses might be 50,000 times more luminous than the Sun. A star of 60 solar masses could be 1,000,000 times brighter. This tremendous luminosity comes at a cost: fuel consumption. The more luminous a star, the faster it burns through its hydrogen reserves. A Sun-like star can fuse hydrogen for about 10 billion years. A 20 solar mass star exhausts its hydrogen in just 8 million years. The most massive stars might last only a few million years from birth to death. Think about that for a moment. These stellar giants, blazing across space with the light of hundreds of thousands of suns, exist for less time than it took for the dinosaurs to evolve and go extinct. They are fleeting by cosmic standards, brilliant, brief, and transformative. As a massive star ages and exhausts the hydrogen in its core, it faces the same issues smaller stars face. The fusion stops, the core begins to contract. But unlike a Sun-like star, which might spend 1 billion years on the red giant branch, a massive star rushes through its post-main sequence evolution. The contracting core heats up, and the star's envelope expands into a red supergiant, vastly larger than a red giant. Betelgeuse, the red star in Orion's shoulder, is a red supergiant. If placed at the Sun's position, it would extend beyond the orbit of Mars, possibly to Jupiter. Its volume is almost beyond comprehension. Billions of times the volume of the Sun, yet containing only about 20 times the Sun's mass. Most of a red supergiant is incredibly diffuse, more vacuum than matter. Meanwhile, the core reaches helium fusion temperatures, about 100 million degrees. Unlike in a Sun-like star, there's no helium flash. The core is not degenerate. Thermal pressure, not quantum mechanical pressure, supports it. Helium fusion begins smoothly, forming carbon and oxygen. For a few million years, the star fuses helium. Then the helium runs out. The core contracts again, heats up again. And if the star is massive enough, above about 8 solar masses, it can reach carbon fusion temperatures, around 600 million degrees. Carbon fusion forms neon and magnesium. It lasts for perhaps a few thousand years. Then neon fusion, forming oxygen and magnesium. This lasts only about a year. Then oxygen fusion, forming silicon, sulfur, and other elements. This lasts for a few months. Finally, silicon fusion, forming iron group elements. This lasts for a single day. Can you sense the acceleration? The desperation? The star is burning through fuels faster and faster in a race against the collapse of its core. Each fusion stage requires higher temperatures, yields less energy per nuclear reaction, and thus exhausts more quickly than the last. During these final stages, the core of the star develops an onion-like structure. At the very center, iron and nickel. Surrounding that, a shell fusing silicon into iron. Outside that, a shell fusing oxygen. Then neon, carbon, helium, and finally hydrogen, burning in nested shells around the inert core. The star is a thermonuclear onion, layers upon layers of fusion, each driven by the heat released by the layers below, all racing toward an inevitable conclusion. Iron, as we mentioned earlier, is the end of the line. Fusing iron doesn't release energy, it requires energy. An iron core is a dead weight, supported only by the thermal pressure generated by the fusion shells surrounding it. As the silicon burning shell continues to convert silicon into iron, the iron core grows, accreting mass like a malignant tumor at the heart of the star. The core's temperature is immense, billions of degrees. Its density is approaching that of atomic nuclei themselves. Atoms, as we know them, don't exist here. The core is a plasma of iron nuclei and free electrons, compressed to densities of millions or billions of grams per cubic centimeter. Yet even at these densities, the core is still supported by thermal pressure, not degeneracy pressure. The electrons have enough energy to maintain thermal motion. The core is in hydrostatic equilibrium, at least for now, but the core is growing. The silicon burning shell feeds it more iron continuously. And there's a limit to how massive an iron core can become before it crosses a point of no return. That limit is, once again, about 1.4 solar masses, similar to the Chandrasekhar limit for white dwarfs, though the exact mechanisms are different. Once the iron core exceeds this mass, thermal pressure can no longer support it. The core becomes marginally stable, teetering on the edge of collapse. And then, in a cascade of physical processes that unfold in less than a second, the core collapses. The star's center implodes, falling inward at speeds approaching a quarter of the speed of light. The outer layers, suddenly unsupported, follow suit, plunging inward. What happens next is one of the most violent events in the universe, a core collapse supernova. The star doesn't just die, it explodes with a fury that briefly rivals the luminosity of an entire galaxy. This is not the gentle ending of a sun-like star, not the slow fade of a white dwarf. This is catastrophic death on a cosmic scale. But I'm getting ahead of the story. Let's linger here for a moment at the precipice, with the iron core teetering on the edge of collapse. The massive star has raced through its life in just a few million years. It has produced its own doom, building an iron core that cannot be sustained. Gravity, patient through all the star's fusion stages, finally claims total victory. In the next chapters, we'll follow the collapse and the explosion, explore the physics of supernovae, and meet the strange objects they leave behind. But for now, breathe in the tension of this moment. A star, millions of times the mass of Earth, hovering on the knife's edge between stability and cataclysm. It's held there only by nuclear reactions outside its core, by fusion shells working furiously to generate heat and pressure. But the iron core continues to grow. And when it reaches the critical mass, nothing in the universe can stop what happens next. The collapse is inevitable, encoded in the physics of matter and gravity. The star's fate is sealed, has been sealed since the moment it was born with too much mass to end gently. The universe, it seems, has dramatic endings reserved for those who live the most intensely. Chapter 7. The Collapse. When fusion stops, the iron core sits at the center of the massive star, growing steadily as the silicon burning shell above converts silicon into iron. The core's temperature is about 8 billion degrees. Its density is approximately 500 billion grams per cubic centimeter, hundreds of times denser than a white dwarf. The core is roughly the size of Earth, but contains about 1.4 times the mass of the Sun. This is the moment before. The core is stable, held up by thermal and electron degeneracy pressure. But it's approaching a critical threshold. When the core mass exceeds about 1.4 solar masses, the Chandrasekhar mass, several processes conspire to trigger collapse. First, the core is so hot and dense that photons, light particles, have extremely high energies. Some of these photons are energetic enough to break apart iron nuclei through a process called photodisintegration. This might sound obscure, but it's crucial. Iron nuclei, which were formed by fusion reactions that released energy, are now being torn back apart by high-energy photons. This process absorbs energy, removing thermal energy from the core. It's as if the star is undoing the work of billions of years of fusion in a few seconds. The energy that was carefully stored in iron nuclei by the fusion process is being forcibly extracted and used to destroy those same nuclei. The core is consuming its own thermal energy to disintegrate itself. Second, something called electron capture begins to occur. At the extreme densities in the core, electrons are pressed against protons in the iron nuclei. Normally, electrons and protons stay separate. They're different particles with different properties. But under these conditions, electrons can be captured by protons, transforming them into neutrons and releasing neutrinos in the process. This might not seem significant, but it has devastating consequences for the core. Remember, the core was being supported partly by electron degeneracy pressure. Remove electrons, and you remove that pressure support. Each electron capture event reduces the pressure holding up the core against gravity. Moreover, the neutrinos produced fly out of the core at nearly the speed of light, carrying away energy. Neutrinos barely interact with matter. They pass through almost anything. In less than a second, these neutrinos carry away a tremendous amount of energy from the core, cooling it. So we have photodisintegration removing thermal energy, and electron capture removing electrons and thus degeneracy pressure while also carrying away energy via neutrinos. The core is losing energy and losing pressure support simultaneously. There's a moment, a brief instant, when the core realizes it can no longer support itself. The pressure drops below what's needed to hold up the overlying mass. And in that instant, the core begins to collapse. The collapse is astoundingly fast. The core implodes at speeds of about 70,000 kilometers per second, roughly a quarter of the speed of light. In less than a second, the core collapses from Earth size to a sphere, perhaps 20 kilometers in diameter. The density increases by a factor of 1 billion or more. This is one of the most dramatic phase transitions in nature, normal matter transforming into something else entirely. Let's slow down and try to comprehend what's happening. As the core collapses, densities rise. The nuclei are crushed together. At some point, the density exceeds that of atomic nuclei themselves, about 2010, circumflex, 1,4 grams per cubic centimeter or 200 trillion grams per cubic centimeter. At this point, the collapsing matter reaches what's called nuclear density. The distinction between individual nuclei breaks down. The matter becomes a sort of nuclear fluid, a soup of neutrons with some protons and electrons mixed in. The neutrons, like electrons before them, are fermions. They obey the Pauli exclusion principle. And at nuclear density, neutron degeneracy pressure kicks in. Suddenly, there's a new source of pressure resisting the collapse. The core's inner regions hit this wall of neutron degeneracy pressure and bounce. Think of it like a ball bouncing on a hard surface, except the ball is the core of a star and the surface is quantum mechanics. The bounce is violent, sending a shock wave propagating outward through the collapsing core. Meanwhile, the outer part of the iron core and all the layers above it are still falling inward. They haven't received the news that the collapse has halted at the center. Information, even in catastrophic astrophysical events, can only travel at the speed of sound in the medium, which is less than the collapse velocity. The infalling material crashes into the outward moving shock wave. The collision is unimaginably violent. Temperatures spike to hundreds of billions of degrees. Matter is compressed beyond nuclear density in the shock front. But here's a problem. The shock wave, despite being launched with tremendous energy, begins to stall. As it propagates outward through the still infalling material, it loses energy. Photodisintegration, the same process that helped trigger the collapse, absorbs energy from the shock. Dissociating iron nuclei into nucleons takes a lot of energy, and the shock is trying to do just that as it moves through iron-rich material. Within a few hundredths of a second, the shock has stalled. It turns into an accretion shock sitting at a radius of a few hundred kilometers, with material falling through it onto the proto-neutron star forming at the center. At this point, it looks like the supernova might fail. The shock doesn't have enough energy to blow off the star's outer layers. The star might simply collapse into a black hole without exploding. But then the neutrinos come to the rescue. Remember, the proto-neutron star at the center is forming, and it's incredibly hot and dense. It's producing neutrinos in vast quantities, about 1, 0, circumflex, 5, 8 neutrinos per second. These neutrinos are streaming outward, and while most pass right through the star without interacting, a tiny fraction, perhaps 1%, deposit their energy into the material behind the stalled shockwave. This doesn't sound like much. 1% of a huge number is still significant, though. The energy deposited by neutrinos heats the material behind the shock, creating a region of hot, buoyant matter. This matter rises, or more accurately, expands outward, driving convection. The convection helps channel neutrino energy into the shock, reviving it. This process, neutrino-driven convection reviving the stalled shock, is thought to be the key mechanism that allows core collapse supernovae to explode. It takes perhaps a half second to a second for the shock to be revived. But once it is, it begins to propagate outward successfully, accelerating as it moves through less dense material. The shock wave plows through the star's outer layers, heating them, accelerating them, dissociating their nuclei, and then refusing them in explosive nucleosynthesis. Elements heavier than iron are formed in this process, created by the immense flux of neutrons in the shock wave. Gold, silver, platinum, uranium, all are formed in supernova, forged in seconds from the neutron-rich environment of the explosion. The shock reaches the star's surface after a few hours. When it does, it breaks out, sending a blast of radiation into space. The star brightens rapidly, becoming as luminous as billions of suns. Material ejected by the explosion expands outward at speeds of tens of thousands of kilometers per second, carrying the star's outer layers into space. This is a core collapse supernova, one of the most energetic events in the universe. The explosion releases about 1, 0, circumflex 5, 1 ergs of kinetic energy in the ejected material. That's about the energy the sun will emit over its entire 10 billion year lifetime, released in seconds. But even more impressive is the neutrino energy. The collapsing core releases about 1, 0, circumflex 5, 3 ergs in neutrinos, about 100 times more energy than the kinetic energy of the explosion. Most of this energy escapes the star in the first few seconds, streaming out at the speed of light, passing through matter almost unhindered. If you could somehow detect all the neutrinos passing through your body from a nearby supernova, say, 1/10,000 light-years away, you'd detect about 1 billion neutrinos passing through you per second for about 10 seconds. Of course, neutrinos interact so weakly that you wouldn't feel anything. But it's a strange thought. The ghostly particles from a dying star, flooding through you, carrying information about the most violent events in nature. At the center of the explosion, buried beneath layers of expanding debris, sits the remnant core, a proto-neutron star, still hot, still settling into equilibrium. Over the next few seconds and minutes, it will continue to cool by neutrino emission, gradually transitioning from a proto-neutron star to a true neutron star. This neutron star is one of the strangest objects in physics, a sphere of matter compressed to nuclear density, governed by physics we still don't fully understand. We'll explore neutron stars in detail in the coming chapters. But first, let's step back and look at the supernova itself from the outside: the light, the expanding shell of gas, the cosmic fireworks that have captivated astronomers for millennia. Chapter 8. Supernovae. Cosmic explosions throughout human history. Bright new stars have occasionally appeared in the night sky, shining where no star had been before. The ancient astronomers of China, Korea, and the Arab world meticulously recorded these guest stars, noting their positions and brightnesses. In 1054 AD, Chinese astronomers observed a star so bright it was visible in daylight for weeks. We now know this was a supernova, the same one that left behind the Crab Nebula, still visible today as an expanding cloud of glowing gas. The word supernova is relatively modern, coined in the 1930s to distinguish these bright stellar explosions from the lesser novae that also appear in the sky. But the phenomenon is ancient and universal. Supernovae have been occurring since the first generation of stars formed, billions of years ago. From Earth, A supernova appears as a sudden brightening of what was either an invisible star or, occasionally, a known star that suddenly becomes vastly brighter. The brightening is dramatic. A supernova can increase in luminosity by a factor of billions, becoming as bright as an entire galaxy for a brief period. At peak brightness, a supernova might outshine all the billions of other stars in its galaxy combined. The light curve of a supernova is characteristic. It rises rapidly, reaching peak brightness in a few days to a few weeks. Then it declines, first quickly, then more gradually, fading over months to years. The exact shape of the light curve depends on the type of supernova and the details of the explosion, but the general pattern is consistent: a rapid rise to a brilliant peak, followed by a long fade. But what we see, the light show, is only a tiny fraction of the energy released by the supernova. Most of the energy, as we noted, escapes in the form of neutrinos, invisible and undetectable except by specialized instruments. The kinetic energy of the explosion, the expanding shell of gas hurtling into space, is the second largest component. The light we see, the photons that travel across space to reach our telescopes, represent less than 1% of the total energy released. Still, that 1% is spectacular. Let's trace where the light comes from. Initially, when the shock wave breaks through the star's surface, the light is generated by the shock itself, the sudden heating of the star's outer layers. This produces an initial flash of ultraviolet and X-ray radiation. But this initial flash is brief, lasting only minutes to hours. As the ejected material expands, it cools and becomes optically thick, opaque to radiation. The photons generated deep in the ejecta can't escape immediately. They're absorbed and re-emitted countless times, gradually diffusing outward. This process takes time, and during this time, the ejecta is expanding and cooling. After a few days, the ejecta has expanded and cooled enough that it becomes transparent to visible light. Now we can see into the ejecta, and the supernova brightens rapidly as photons trapped inside begin to escape. This is when the supernova reaches peak brightness. But there's a question. If the ejecta is expanding and cooling, why does the brightness plateau and then decline slowly rather than dropping immediately? The answer is radioactive decay. The explosion synthesizes radioactive isotopes, particularly nickel-56, which decays to cobalt-56, which in turn decays to stable iron-56. These decay processes release energy in the form of gamma rays, which are absorbed by the ejecta and re-emitted as visible light. This radioactive heating powers the supernova's light for months after the explosion. As the radioactive isotopes decay away, the light fades. The rate of decline in brightness is directly related to the half-lives of the radioactive isotopes involved. For type II supernovae, those from core collapse of massive stars, the decline is powered first by nickel-56 half-life 6 days, then by cobalt-56 half-life 77 days. Astronomers can actually measure the amount of nickel-56 synthesized in a supernova by carefully studying its light curve. This tells us about the conditions in the explosion and helps test models of supernova physics. Not all supernovae are created equal. There are different types, classified originally by their spectra, the patterns of light they emit at different wavelengths. Typeset supernovae show hydrogen in their spectra. These are core collapse supernovae from massive stars that retain their hydrogen envelopes. Type Ib and Eq supernovae lack hydrogen. These are also thought to be core collapse events, but from stars that lost their hydrogen envelopes before exploding, perhaps through strong stellar winds or mass transfer to a companion star. Type Ia supernovae are different. They show no hydrogen and no helium, and their light curves are remarkably consistent. Type Ia supernovae are thought to originate from white dwarfs in binary systems that have accreted matter from a companion and exceeded the Chandrasekhar mass limit. The white dwarf undergoes thermonuclear explosion, not a core collapse, but a runaway fusion reaction that completely disrupts the white dwarf. These Type Ia supernovae are important in cosmology. Because they all seem to reach similar peak brightnesses with some calibration, they can be used as standard candles to measure distances to faraway galaxies. This technique was used in the late 1990s to discover that the expansion of the universe is accelerating, a finding that led to the concept of dark energy and earned a Nobel Prize. But let's return to core collapse supernovae, which are our focus tonight. The explosion ejects the star's outer layers into space at tremendous speeds, 10,000 to 30,000 kilometers per second. This material crashes into the surrounding interstellar medium, creating a shock wave that heats gas to millions of degrees. Over time, this expanding shell of ejected material forms a supernova remnant, a complex structure of shocked gas, magnetic fields, and high-energy particles. The remnant can remain visible for thousands of years, gradually mixing the supernova ejecta with the interstellar medium. Famous supernova remnants include the Crab Nebula from the 1054 supernova, the Vela supernova remnant, about 11,000 years old, and Cassiopeia A, about 350 years old. Each is unique, shaped by the properties of the progenitor star, the nature of the explosion, and the structure of the surrounding interstellar medium. These remnants are beautiful when viewed through telescopes, especially in X-rays and radio waves. They're also scientifically valuable, providing laboratories for studying extreme physics, shock waves, particle acceleration, magnetic field amplification. Some supernova remnants accelerate particles to near light speeds, creating cosmic rays that stream through the galaxy. The supernova also enriches the interstellar medium with heavy elements. All the carbon, oxygen, silicon, iron, and heavier elements forged in the star's core and in the explosion itself are ejected into space. This material will eventually be incorporated into future generations of stars and planets. You are made of supernova ejecta. The atoms in your body were created in stars that lived and died before the sun was born. Your calcium, your iron, your zinc, all are supernova products, forged in the final moments of massive stars and dispersed into the galaxy by supernova explosions. There's a poetic symmetry to it. Stars give birth to planets, and planets give birth to life. But stars themselves are born from the remains of previous stars. The universe recycles, transforming matter through stellar life cycles, creating complexity and diversity from the simple hydrogen and helium produced in the Big Bang. Supernovae are essential to this cycle. Without them, the galaxy would be composed only of hydrogen and helium. There would be no rocky planets, no water, no complex chemistry, no life. Supernovae are destructive, yes, catastrophically so. But they're also creative, enriching the cosmos with the elements necessary for worlds and life. From our safe distance, we can appreciate supernovae as both science and spectacle. They're the laboratory where elements are born, the mechanism that enriches galaxies, and the phenomenon that leaves behind the strangest objects in the universe, neutron stars and black holes. As we move forward, we'll turn our attention to the remnant core left behind by the supernova. The expanding shell of gas is spectacular, but the core is where the truly strange physics resides. In the center of the explosion, compressed to unimaginable densities, stabilized by neutron degeneracy pressure, lies a neutron star, our next destination in this cosmic journey. Chapter 9. Neutron stars. Islands of nuclear matter. Imagine compressing the entire mass of the Sun into a sphere just 20 kilometers across. The resulting object would have a density of about 1 billion tons per teaspoon. Neutrons would be packed together so tightly that the entire star would have the density of an atomic nucleus. This is a neutron star, the remnant core left behind by a core collapse supernova. Neutron stars are almost absurdly extreme. They represent matter in a state that cannot exist anywhere else in the universe except possibly in the very cores of the most massive neutron stars. To understand them, we need to push our physical intuition to its limits and beyond. Let's start with the basics. After the supernova explosion, the core of the massive star has collapsed to nuclear density and has bounced, launching the shock wave that drove the explosion. But the core itself remains, settling into a new equilibrium. This core is initially very hot, billions of degrees, and is still stabilizing. Over a few seconds, it cools by emitting neutrinos, losing energy rapidly. The proto-neutron star transitions to a true neutron star, a sphere of matter in equilibrium, supported against gravitational collapse by neutron degeneracy pressure. Just as white dwarfs are supported by electron degeneracy, neutron stars are supported by neutron degeneracy. But neutrons are about 2,000 times more massive than electrons, and the densities in neutron stars are 1 billion times higher than in white dwarfs. The physics is similar in principle, but vastly more extreme in practice. A typical neutron star has a mass between 1.4 and 2.0 solar masses, though the exact range is still debated. The radius is about 10 to 12 kilometers. This gives an average density of a few times 10 circumflex, 4 grams per cubic centimeter, roughly the density of an atomic nucleus. To give you a sense of this, if you could bring a cubic centimeter of neutron star material to Earth and somehow prevent it from exploding due to the sudden lack of gravity, it would weigh about 400 million tons. That's roughly the mass of all humans on Earth, compressed into a sugar cube. The gravitational field at the surface of a neutron star is about 200 billion times stronger than Earth's. If you could stand on a neutron star, you can't, but imagine, you'd weigh about 200 billion times more than you do on Earth. The escape velocity is about 150,000 kilometers per second, about half the speed of light. Time itself is affected. Clocks on the surface of a neutron star run about 30% slower than clocks far from the star, due to the intense gravitational time dilation predicted by general relativity. Photons climbing out of the neutron star's gravity will lose about 2.030% of their energy, their wavelengths stretched by the gravitational redshift. But let's dig deeper into the structure of a neutron star, because it's not simply a uniform ball of neutrons. The interior has layers, each with different properties. At the surface, there's a thin atmosphere, perhaps a few centimeters thick, composed of whatever elements are present. Due to the intense gravity, heavier elements sink, so the surface might be primarily iron or even heavier elements if the neutron star has accreted material. Below the atmosphere is a solid crust, where atomic nuclei are arranged in a crystal lattice, surrounded by a sea of electrons. Wait, a solid crust? How can something at billions of degrees be solid? The answer is pressure. At the densities in a neutron star's crust, millions to billions of grams per cubic centimeter, the thermal energy is less than the potential energy associated with the arrangement of nuclei. The nuclei form a crystal lattice because that's the lowest energy configuration. Even though the temperature is high, it's solid for the same reason a diamond is solid. The binding forces are much stronger than the thermal motion. As you go deeper, the density increases, and the nuclei become increasingly neutron-rich. At some point, neutrons start to drip out of the nuclei, forming a neutron fluid that permeates the lattice. This is called the neutron drip line. Below this, the crust consists of neutron-rich nuclei embedded in a sea of free neutrons and some electrons. Near the base of the crust, the nuclei take on bizarre shapes. At these densities, it becomes energetically favorable for the nuclei to form rods, sheets, and even more exotic geometries, collectively called nuclear pasta. There are gnocchi spherical nuclei, spaghetti rod-like nuclei, lasagna planar sheets, and even inverse structures where the nuclear matter forms a continuous phase with bubbles or tubes of less dense matter. This nuclear pasta phase is thought to be extremely rigid, possibly the strongest material in the universe. Below the crust, at about half the radius of the neutron star, the density reaches nuclear density, and we enter the core. Here, the distinction between individual nuclei disappears. The core is a fluid of neutrons with a smaller number of protons, electrons, and possibly other particles. The physics of the core is uncertain. We don't know for certain what happens to matter at these densities because we can't reproduce these conditions in terrestrial laboratories. The Large Hadron Collider can achieve high energies, but not the sustained high densities present in neutron stars. Nuclear physics experiments probe the interactions of nuclei, but extrapolating to bulk nuclear matter at several times nuclear density is uncertain. There are various theoretical possibilities. The core might be primarily neutrons with some protons and electrons, as the name suggests. But at higher densities, exotic particles might appear. Hyperons, particles containing strange quarks, might form. Meson condensates, collective quantum states of certain particles, could exist. In the very center of the most massive neutron stars, there might even be deconfined quark matter, where the quarks that make up neutrons and protons are no longer bound inside individual particles but exist as a free fluid. This quark matter, if it exists, represents a different phase of matter, a quark-gluon plasma or a crystalline quark state. The transition from hadronic matter neutrons, protons, etc. to quark matter would be a phase transition, analogous to ice melting into water or water boiling into steam, but occurring at densities and temperatures far beyond terrestrial experience. The equation of state of nuclear matter, the relationship between density, pressure, and other thermodynamic quantities, is one of the major uncertainties in neutron star physics. Different equations of state predict different maximum masses for neutron stars. Some models allow neutron stars up to about 2.5 solar masses. Others predict a lower maximum, around 2.0 solar masses. Observations of neutron star masses can help constrain these models. In recent years, astronomers have measured the masses of several neutron stars with high precision. The most massive confirmed neutron stars have masses around 2.0 solar masses, which rules out some of the softer equations of state, those that predict lower maximum masses. There's also a limit to how massive a neutron star can be before it collapses into a black hole. This maximum masses is set by the equation of state and is called the Tolman-Oppenheimer-Volkoff-Tovey limit, analogous to the Chandrasekhar limit for white dwarfs. If a neutron star exceeds this mass, even neutron degeneracy pressure cannot support it, and it must collapse to a black hole. The exact value of the TOV limit is uncertain, but it's probably between 2.0 and 2.5 solar masses. Some neutron stars might be born near this limit and could be pushed over it by accreting material, triggering collapse to a black hole. This might be observable as a sudden disappearance of the neutron star's emission, though it would be hard to distinguish from the neutron star simply becoming too faint to observe. Neutron stars also have remarkable magnetic fields. Many neutron stars have field strengths of about 1,0 circumflex 1,2 Gauss, a trillion times stronger than Earth's magnetic field. Some, called magnetars, have fields up to 1,0 circumflex 1,5 Gauss, the strongest magnetic fields known in the universe. These magnetic fields can affect the star's structure and evolution. They store enormous amounts of energy, and their decay can heat the star or power various forms of emission. Magnetars, in particular, are powered primarily by their magnetic fields rather than by rotation or accretion, and they can emit powerful bursts of X-rays and gamma rays. The combination of rapid rotation, strong magnetic fields, and extreme density makes neutron stars some of the most fascinating objects in astrophysics. They are natural laboratories for extreme physics, testing general relativity, nuclear physics, quantum electrodynamics, and other theories in regimes we cannot access on Earth. From a distance, though, a neutron star is just a small, dense object, cooling and fading. Many are invisible, dark spheres of nuclear matter drifting through the galaxy. But some make themselves known in spectacular ways, through their rotation or their magnetic fields or their interactions with companion stars. These we call pulsars, magnetars, X-ray binaries, categories we'll explore in the next chapter. For now, rest in the strange wonder of neutron stars themselves, spheres of nuclear matter, the densest stable objects in the universe, balanced on the edge between stability and collapse into black holes. They represent the ultimate compression of matter, the last stage before gravity wins completely. And yet they exist, patient and stable, governed by physics we're still working to fully understand. Chapter 10. Pulsars and the Spinning Dead. In 1967, Jocelyn Bell, then a graduate student at Cambridge, was analyzing data from a radio telescope designed to observe quasars. She noticed something odd: a regular pulse of radio waves occurring with astonishing precision every 1.337 seconds. At first, the signal was so regular that the team joked about it being a signal from extraterrestrials, even labeling it LGM-1 for little green men. But as more of these pulsing sources were discovered, it became clear they were natural astrophysical objects. Within a year, astronomers had identified them as rapidly rotating neutron stars, their pulses caused by beams of radiation sweeping across Earth like a cosmic lighthouse. These objects are pulsars, pulsating radio sources, and they reveal neutron stars in a way that might otherwise remain hidden. Let's explore how they work and what they tell us about the physics of these extreme objects. When a massive star's core collapses to form a neutron star, two properties are conserved: angular momentum and magnetic flux. The original star was rotating, perhaps slowly, and it had a magnetic field, perhaps similar in strength to the Sun's. But as the core collapses by a factor of about 100,000 in radius, both the rotation rate and the magnetic field strength increase dramatically. Rotation speeds up due to conservation of angular momentum. Think of a figure skater pulling in their arms to spin faster. The same principle applies, but taken to an extreme. A core that was rotating once every few days might end up rotating many times per second after collapse. The fastest known pulsar rotates 716 times per second. That's a sphere the size of a city, with more mass than the sun, spinning faster than a kitchen blender. Magnetic fields strengthen due to conservation of magnetic flux. If the field is frozen into the star's material, compressing the star amplifies the field. A field of a few Gauss in the original star might become a trillion Gauss in the neutron star. This combination, rapid rotation and strong magnetic field, creates the pulsar phenomenon. The neutron star's magnetic axis is typically misaligned with its rotation axis, just as Earth's magnetic North Pole doesn't coincide with the geographic North Pole. As the star rotates, its magnetic field rotates with it. Charged particles, electrons and positrons, are accelerated by the magnetic field, spiraling along field lines and emitting radiation. This radiation is beamed along the magnetic poles. If the magnetic pole happens to be pointing toward Earth at some point in the star's rotation, we see a pulse of radiation. If not, we see nothing. As the star rotates, the beam sweeps across space like a lighthouse beam, and we see pulses separated by the rotation period. The precision of these pulses is extraordinary. The best pulsars are more stable timekeepers than atomic clocks over periods of months to years. Astronomers can predict the arrival time of pulsar pulses to microsecond precision. This precision has practical applications. Arrays of pulsars are being used to search for gravitational waves, low-frequency ripples in spacetime that would cause slight variations in pulse arrival times. But pulsars don't maintain their rotation forever. They're spinning down, gradually losing angular momentum and rotational kinetic energy. This energy loss is caused by the magnetic field, which acts like a brake on the star's rotation. Here's how. The rotating magnetic field accelerates charged particles, which requires energy. This energy comes from the star's rotation. Additionally, the rotating magnetic field generates electromagnetic waves light that carry energy away. Both processes drain rotational energy, causing the pulsar to spin down over time. The rate of spin down can be measured very precisely by timing the pulses. Young pulsars spin down faster, old pulsars spin down more slowly. By measuring the spin down rate, astronomers can estimate the pulsar's age and the strength of its magnetic field. The Crab pulsar, the neutron star left behind by the 1054 supernova, rotates 30 times per second and is slowing down at a measurable rate. Given its current spin down rate, astronomers calculate that it will slow to 1 rotation per second in about 10,000 years, though the actual evolution is more complex. As pulsars age and slow down, they eventually become too slow to generate radio pulses efficiently. After perhaps 100 million years, they turn off as pulsars, though the neutron star itself remains. It simply becomes invisible at radio wavelengths. Astronomers estimate that there might be hundreds of millions of inactive neutron stars in our galaxy, invisible remnants of ancient supernovae. Some pulsars, though, experience a second life. If a neutron star is in a binary system and begins accreting matter from a companion star, the infalling matter carries angular momentum. This can spin the neutron star back up, reviving it as a pulsar. These recycled pulsars, also called millisecond pulsars, can rotate hundreds of times per second. They've been spun up by accretion, gaining angular momentum from their companion. Millisecond pulsars are particularly interesting because they're very stable rotators. Their rapid spin and old age, they've had time to spin down and then be spun back up, make them excellent clocks for testing fundamental physics. Some pulsars exhibit glitches, sudden increases in rotation rate. These occur perhaps once every few years in young pulsars. The mechanism is thought to involve the neutron star's interior structure. The superfluid interior, yes, neutron stars have superfluid cores rotate slightly faster than the crust. Occasionally, the crust and interior recouple, transferring angular momentum from the interior to the crust and causing a sudden spin-up. Glitches tell us about the star's internal structure, the rigidity of the crust, the properties of the superfluid core, and the coupling between different layers. They're windows into the interior of neutron stars, revealing physics we can't study any other way. Not all neutron stars are pulsars, and not all neutron stars emit primarily radio waves. Some are observed as X-ray sources, particularly in binary systems where they're accreting matter from a companion. The infalling matter heats up to millions of degrees, emitting X-rays. These X-ray binaries are laboratories for studying accretion, magnetic fields, and the behavior of matter in strong gravity. Some neutron stars are magnetars, with magnetic fields so strong they dominate the star's evolution. Magnetars emit primarily in X-rays and gamma rays, powered by the decay of their magnetic fields. They occasionally produce giant flares, bursts of gamma rays so intense they can affect Earth's ionosphere from thousands of light years away. The strongest magnetar flare ever recorded occurred in 2004 from a magnetar called SGR 180620, about 50,000 light-years away. The flare released more energy in 1/10 of a second than the Sun emits in 150,000 years. If such a flare occurred from a magnetar just 10 light-years away, it could cause a mass extinction on Earth. Fortunately, there are no magnetars that close to us. Pulsars, X-ray binaries, magnetars, these are different manifestations of neutron stars, the same underlying objects observed under different conditions. The variety is a testament to the complexity of neutron star physics and the range of environments in which they're found. Throughout all of this, remember, we're talking about objects the size of a city, with more mass than the Sun, rotating up to hundreds of times per second, with magnetic fields trillions of times stronger than Earth's, composed of matter at nuclear density. They are, quite simply, the most extreme objects we know of, short of black holes. And even neutron stars have a limit. Spin them up too much, or add enough mass, and even neutron degeneracy pressure cannot support them. They collapse further, undergoing a final transformation into the most mysterious objects in the universe, black holes. That's our destination in the next chapter, the ultimate endpoint of stellar death, where gravity wins completely and utterly. Chapter 11. Black Holes and the Ultimate Fate. There is a point beyond which matter cannot resist gravity. Not electron degeneracy. Not neutron degeneracy. No pressure known to physics can halt the collapse. When a stellar core exceeds about 2 to 3 solar masses, depending on the exact equation of state of nuclear matter, it collapses past the neutron star stage, crushing down beyond nuclear density, beyond any known form of matter, until it reaches a state where the gravitational field becomes so strong that not even light can escape. This is a black hole, the ultimate endpoint of gravitational collapse, an object so extreme that it warps space-time around itself, creating a one-way boundary called an event horizon. Black holes represent a kind of defeat for physics. Inside the event horizon, our equations break down. We don't know what happens to matter that falls past that boundary. We can describe the external properties of black holes with precision, using general relativity, but the interior remains mysterious, cloaked by the horizon. Let's approach black holes carefully, starting with the formation process. When a very massive star, perhaps more than 20 or 25 solar masses, collapses, the core might be too massive to form a stable neutron star. The bounce that launches the supernova shock wave might not be strong enough, or the shock might fail to eject the outer layers entirely. Material falls back onto the protoneutron star, adding mass. If enough mass falls back, the neutron star exceeds the maximum mass and collapses further. There's no stopping this collapse. Neutron degeneracy pressure has been overcome. The core contracts, and as it does, the gravitational field grows stronger. At some point, the surface of the collapsing core crosses a critical radius called the Schwarzschild radius. The Schwarzschild radius is given by a remarkably simple formula. R is equal sign 2g/g, where g is the gravitational constant, m is the mass, and c is the speed of light. For a mass of a few solar masses, the Schwarzschild radius is only a few kilometers. Once the surface of the collapsing core crosses this radius, an event horizon forms. Light emitted from inside the horizon curves back inward. It cannot escape. The object has become a black hole. From outside, the collapse appears to slow down and freeze at the horizon due to gravitational time dilation. Photons emitted from the surface become increasingly red-shifted, their wavelengths stretched to infinity as the surface approaches the horizon. The collapsing star effectively fades from view, becoming darker and darker, asymptotically approaching invisibility. But from the perspective of the infalling matter, nothing special happens at the horizon. There's no barrier, no wall. The matter simply continues to fall inward, accelerating toward the center. Inside the horizon, all paths lead inward. It's impossible, even in principle, to move outward, because doing so would require exceeding the speed of light, which is forbidden. At the center of the black hole, general relativity predicts a singularity, a point of infinite density where the laws of physics break down. We don't know if the singularity is physically real or if quantum effects, which we currently don't understand in this regime, prevent true infinite density. This is one of the great unsolved problems in theoretical physics. Understanding what happens at the center of a black hole requires a theory of quantum gravity, which we don't yet have. But we can describe the exterior of black holes with great precision. A black hole has only three properties: mass, angular momentum, spin, and electric charge. All other information about the infalling matter, its composition, structure, history, is lost. This is summarized by the phrase black holes have no hair, meaning they have no additional distinguishing features. Most astrophysical black holes have negligible electric charge. Matter is mostly neutral, and any net charge would be neutralized by attracting opposite charges. So we typically only consider mass and spin. A spinning black hole is described by a more complex solution to Einstein's equations, called the Kerr metric. The event horizon of a spinning black hole is surrounded by another surface called the ergosphere, where space-time itself is dragged around by the black hole's rotation. In the ergosphere, it's impossible to remain stationary. Everything must orbit in the direction of the black hole's spin. The maximum spin for a black hole is set by the condition that the event horizon doesn't disappear. A maximally rotating black hole has an angular momentum parameter of an equal sign 1 in certain units. Faster spin would eliminate the horizon, exposing the singularity, a naked singularity, which is thought to be forbidden by the cosmic censorship conjecture, though this remains unproven. Black holes can grow by accreting matter or by merging with other black holes. When a black hole accretes matter, the infalling material doesn't just disappear quietly. It typically forms an accretion disk, heated by friction to millions of degrees, emitting X-rays and sometimes powerful jets of particles moving at nearly the speed of light. These jets are among the most energetic phenomena in the universe. They can extend for millions of light years, powered by the rotational energy of the black hole extracted through magnetic fields in the accretion disk. The exact mechanism, how energy is extracted from the black hole and channeled into jets, is an active area of research involving complex interactions between magnetic fields, plasma physics, and general relativity. Stellar mass black holes, those formed from collapsed stars, have masses from a few to perhaps 100 solar masses. They're invisible unless they're accreting matter from a companion star or unless they're detected through their gravitational effects. One way to detect stellar mass black holes is in binary systems. If a black hole orbits a normal star, the star's motion reveals the presence of an unseen massive companion. By measuring the orbital parameters, astronomers can determine the mass of the companion. If that mass exceeds the maximum mass for a neutron star, the companion must be a black hole. The first confirmed stellar mass black hole was Cygnus X1, identified in the early 1970s. It's a binary system where a massive blue supergiant orbits an unseen companion with a mass around 15 solar masses, too massive to be a neutron star. X-rays from the system come from an accretion disk around the black hole. Since then, dozens of stellar mass black holes have been identified, mostly in binary systems, mostly in our own galaxy or nearby galaxies. They're the remnants of massive stars, the final stage of stellar evolution for the most massive stars. But there's another population of black holes, discovered more recently, intermediate mass black holes. These have masses of hundreds to thousands of solar masses and might form in dense star clusters through repeated mergers of stars and stellar remnants. The existence of intermediate mass black holes is still debated, but there are a few candidates. And then there are supermassive black holes. millions to billions of times the mass of the Sun found at the centers of most galaxies. These are not stellar remnants. They're thought to have formed through different processes, perhaps from the direct collapse of massive gas clouds in the early universe or through the merger of many smaller black holes. But that's a story beyond the scope of stellar death. For our purposes, stellar mass black holes represent the ultimate endpoint of massive stars. They're the final stage when fusion ceases, when degeneracy pressure fails, when matter collapses without limit. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO detected gravitational waves from the merger of two stellar mass black holes. This confirmed a century-old prediction of general relativity and opened a new window on the universe. Since then, dozens of black hole mergers have been detected, teaching us about the population of stellar mass black holes, their spins, their masses, and how they form and evolve. One surprising finding: some of the black holes detected by LIGO are more massive than expected from traditional stellar evolution models. Black holes of 30, 40, 50 solar masses have been observed. This suggests either that very massive stars can form black holes with little mass loss, or that black holes can grow by mergers more efficiently than previously thought. Black holes also evaporate, according to quantum mechanics. Stephen Hawking predicted in the 1970s that black holes emit radiation due to quantum effects near the horizon. This Hawking radiation is incredibly faint for stellar mass black holes. The temperature is about a millionth of a Kelvin, far colder than the cosmic microwave background. So stellar mass black holes are actually absorbing more radiation from the universe than they emit. But given enough time, far more than the current age of the universe, black holes will evaporate. A solar mass black hole will take about 1.0 circumflex 6-7 years to evaporate. That's a number so large it's hard to comprehend, far longer than the age of the universe, far longer than the time for all stars to burn out and cool. Black holes are, in a practical sense, eternal. So in the far future, after all stars have died, after white dwarfs have cooled to black dwarfs, after neutron stars have cooled to invisibility, the universe will be populated primarily by black holes, and even they will eventually evaporate, leaving behind what? Photons? Dilute gas? Empty space? This is the heat death of the universe, a state of maximum entropy where no further evolution is possible. But that's trillions upon trillions of years away. For now, black holes are active, dramatic objects, powering jets, accretion disks, mergers detected as gravitational waves. They're the ultimate transformation of matter, the endpoint of gravitational collapse, the objects that mark the boundary beyond which our knowledge fades. They represent both a conclusion and a mystery, the end of the star's story, but the beginning of questions we don't yet know how to answer. Chapter 12. Our cosmic perspective. We've traveled a long journey tonight, from the first signs of stellar aging to the ultimate endpoints of stellar death. We've witnessed gentle fades into white dwarf crystallization and catastrophic explosions that briefly rival galaxies in brightness. We've explored quantum mechanics operating on stellar scales and encountered objects so dense, so extreme, that they challenge our understanding of matter and space. Take a moment to reflect on the variety of stellar deaths. Small stars cool slowly into carbon diamonds. Sun-like stars shed their outer layers in glowing nebulae, leaving behind crystalline cores. Massive stars explode violently, forging heavy elements and leaving neutron stars or black holes. The universe, it seems, has many endings for its stars, each appropriate to the star's mass and nature. There's something profound about understanding these processes. Stars seem eternal from our limited perspective. Human lifetimes are so brief compared to stellar timescales. Yet every star is mortal, burning through its fuel, approaching an inevitable end. This isn't cause for sadness, but for perspective. The universe is dynamic, ever-changing, transforming matter from one form to another across cosmic cycles. You are connected to this story in an intimate way. The atoms that make up your body, the molecules in the air you breathe, the elements in the earth beneath you, all were forged in stellar interiors and dispersed by dying stars. You exist because stars died. The calcium in your bones was created in a supernova. The iron in your blood was synthesized in a stellar core. The oxygen you're breathing was formed in stars and released when those stars shed their outer layers or exploded. Carl Sagan famously said, "We are made of star stuff." This is not metaphor but literal truth. You are the product of countless stellar life cycles, generations of stars that lived, died, and enriched the cosmos with the elements of complexity. Every breath you take connects you to the death of stars. Our sun will die someday, though not for billions of years. It will swell into a red giant, perhaps engulfing Earth. It will shed its outer layers in a planetary nebula, beautiful and ephemeral. The core will cool as a white dwarf, crystallizing over timescales longer than the universe has currently existed. But this future is distant, and life on Earth will have long since evolved or disappeared or spread to other worlds. The death of the sun is not an immediate concern, but a reminder of change, of the finite nature of all things, even stars. Other civilizations, if they exist among the billions of stars in our galaxy, face the same eventual fate. Their home stars will age and die. Perhaps some civilizations learn to migrate, moving from world to world as their stars evolve. Perhaps some learn to engineer stellar processes, extending their star's life or carefully managing its death. These are speculations, of course, but they remind us that the death of stars is a challenge the cosmos presents to any long-lived civilization. For now, we can observe stellar deaths from a safe distance, learning from their light and their remnants. Each supernova we observe teaches us about physics in conditions we cannot reproduce. Each pulsar we time tests general relativity and nuclear physics. Each black hole we detect through gravitational waves reveals the population of stellar remnants and how they evolve. The study of stellar death is also about origins. Supernovae trigger star formation, their shock waves compressing gas clouds and initiating collapse. Neutron star mergers create gold, platinum, uranium, and other heavy elements. White dwarfs exploding as Type Ia supernova have taught us that the universe's expansion is accelerating, leading to the discovery of dark energy. Death and birth are intertwined in the cosmos. Stars die, enriching the interstellar medium. That enriched gas collapses to form new stars and planets. Those planets can host life. That life is made possible by the elements forged in previous generations of stars. The cycle continues, building complexity, creating diversity. We've also touched on mysteries, things we don't yet understand. The exact equation of state of nuclear matter in neutron stars. The nature of quark matter at ultra-high densities. What happens inside a black hole's event horizon. How the most massive stars produce such unexpectedly massive black holes. The mechanisms that power the brightest supernovae. These unknowns are not failures of science but frontiers, invitations to keep exploring, observing, calculating. Each question answered raises new questions. Each observation tests theories and sometimes reveals surprises. Perhaps someday we'll understand stellar death completely, down to the last detail. Or perhaps the universe will always retain some mysteries, some aspects that resist full understanding. Either way, the journey is worthwhile. The effort to comprehend the cosmos, to see patterns in the chaos, to understand how matter and energy transform across time. As you prepare for sleep, let these cosmic processes settle into your thoughts. Imagine white dwarfs cooling silently in the dark spaces between stars. Picture neutron stars spinning hundreds of times per second, beaming radiation into the void. Visualize black holes warping space-time around themselves, absorbing everything that crosses their horizons. These objects exist right now, scattered through our galaxy and beyond. The universe is filled with stellar remnants, the tombstones of ancient stars, each with its own story of life and death. Some are active, violent, observable. Others are quiet, fading, invisible except through indirect effects. The night sky you see is filled with stars at every stage of life. Some are being born, condensing from gas clouds. Some are in their stable middle age, like our sun. Some are aging, evolving into red giants or supergiants. And some are dying or have already died, leaving behind white dwarfs, neutron stars, or black holes. You can't see most of these remnants directly. White dwarfs are too faint unless they're very close. Neutron stars are tiny and dark unless they're pulsars or accreting matter. Black holes are, by definition, invisible. But they're there, outnumbered by living stars, but numerous enough, hundreds of millions of stellar remnants in our galaxy alone. In a sense, we live in a cosmic graveyard, surrounded by the remnants of stars that died before the sun was born. But it's not a sad place. It's a place of transformation, where matter undergoes its most extreme changes, where physics pushes to its limits, where the universe demonstrates both its violence and its creativity. The death of stars is not an ending, but a transition. Matter transforms, but doesn't vanish. Energy radiates into space, available to warm worlds or ionize gas or drive new generations of star formation. Elements spread, mixing with the interstellar medium, available to be incorporated into new stars, new planets, new possibilities. Nothing is truly lost in the universe. It just changes form. This is the first law of thermodynamics, the conservation of energy. But it's also a deeper principle. The universe recycles, endlessly transforming matter and energy, creating complexity through cycles of birth and death. As your mind drifts towards sleep, carry with you this perspective. You are part of this cosmic cycle. You exist because stars lived and died. The matter in your body has been through multiple stellar life cycles, forged in ancient furnaces, dispersed by ancient explosions, reconstituted in our solar system, incorporated into a planet, and eventually into you. You are star stuff, made conscious, contemplating the deaths of stars. It's a remarkable position to hold, to be part of the universe, and to understand, even partially, the processes that created you. Let that understanding be a source of comfort. You are connected to the cosmos in the most fundamental way. When you look at the stars, you're seeing your own origins, your own composition. The carbon in your cells came from helium fusion in red giants. The iron in your blood came from core collapse, supernovae. The gold in any jewelry you might wear came from neutron star mergers. Every atom tells a story of stellar death, and those atoms will continue their journey long after you. They'll be returned to the environment, eventually mixing back into the biosphere, and someday, far in the future, they might be incorporated into other structures, other processes, perhaps even other forms of life. The cycle continues. Stars die, but their matter persists, transforming, cycling through the cosmos. You're a temporary arrangement of atoms, a brief eddy in the great flow of matter through space and time. But while you exist, you can contemplate this flow, understand it, appreciate the journey that brought you into being. So rest easy. The universe is vast and strange, filled with extremes and mysteries, but it's also comprehensible, at least in part. We can trace the paths of matter, understand the physics of death and transformation, see the patterns that connect the small and the large, the living and the dead. Stars die in fire or fade in silence. They leave behind crystals, neutron spheres, warped spacetime. They seed the cosmos with elements, trigger new births, shape galaxies. They are mortal, like you, but their matter lives on, transformed, recycled, eternal in its essence if not its form. As you drift toward sleep, let the rhythm of the cosmos carry you. Imagine the slow cooling of white dwarfs over billions of years. Feel the rapid pulses of pulsars spinning hundreds of times per second. Sense the gravitational waves from merging black holes, ripples spreading across space at the speed of light. The universe is humming with these processes, right now, all around you. Stars are dying as you sleep, somewhere in the cosmos. New remnants are forming. Old remnants are cooling, fading, merging. The cycle continues, indifferent to human timescales, operating on its own vast rhythms. You've learned about stellar death tonight. You've understood something profound about the cosmos and about your own nature. As you sleep, these ideas can settle, integrate, become part of how you see the universe. Tomorrow, when you wake, the stars will still be there, living and dying according to the laws of physics. And you'll be here, a part of the cosmos, made of star stuff, contemplating the deaths of stars. Sleep well. Dream of supernovae, if you dream at all. And know that in understanding the deaths of stars, you've touched something fundamental about existence itself. The cycle of birth, life, death, and transformation that connects all matter, from the smallest atoms to the largest stars, across all of space and time. Good night.